Well, hi everybody. Welcome back for the practical session of today's bioinformatics class. We are on day 4 of 5 in our R training course, and today we're finally going to get down to some graphing, because I think one of the reasons why people bother learning R is that they want to develop beautiful graphics for their posters and for their publications, and for their theses and dissertations too. R is one of the best visualization environments for this, and we are going to work through visualizing data using base graphics and using Ggplot. Now, I have already mentioned that R comes with a lot of functionality built in just from the word go. You remember when we created factors, for example, we could run the plot function on them and immediately get a histogram out of them. And base graphics are pretty good, but a lot of people have decided that the grammar of graphics approach is a really powerful way for us to add new layers to images, to make compound graphics that really allows us to do more than what the base graphics that ship with R can let us do. So hopefully you have already had the chance to install the Ggplot 2 library on your machine. If you have not, I hope you have network access, because it's going to take a little bit of time to do. Ggplot, the Grammar of Graphics plotter, is part of the Tidyverse universe, the set of libraries that have come to really dominate a lot of data sciences these days. So Ggplot 2 is a really, really standard library for people to use. Now, because I've already installed it, I'm going to go ahead to just run library Ggplot 2. So I would note that, let me see, pull this up again. Okay, there we go. That we've already shown this with things like read Excel, but having installed a package onto the R install doesn't mean that you immediately get to use it. Until you run the library command, the library function on that library, the functions within it are not available to you. So if you're finding that the instructions are failing in the script, it could be that you just haven't run the library command up front. If you run library on some library that you don't have installed, however, you're going to get an error from that. Now, it might seem at first that R didn't like what I just did. You see how it has all this stuff about registered S3 methods overwritten by. You might find that you're confused by that and think, oh, an error has happened. It hasn't, actually. In this case, Ggplot 2 has a bunch of functions inside it that are that have the same name as functions that are already in place for R or some of the other libraries I have in place. So here it's just notifying me that Ggplot 2 has some methods built into it that use the same name as function calls that are already in place. So we're not going to need to worry about that. It's just letting us know that they exist. Okay, so helpfully, Ggplot 2 is also giving us some demonstration data sets to work with. And the iris data set is one of the most frequently used. You will find any number of tutorials online that make use of this iris data set. So I want to walk through that for just a moment. Iris is a characterization of iris species. Basically, 50 different plants of the setosa, the versicolor, and the virginica plants were all profiled on 4 variables. So does everyone remember the difference between a sepal and a petal? A sepal and a petal. Okay, all right. So that was very soft. I don't think that was picked up on the video, but I'm going to give my 7th grade biology version of this, which is to say that the sepals are specialized. Oh, I have a plant biologist looking at me now. I'm worried. Okay, all right. Well, I think of sepals as specialized petals that are around the flower. Is that terrible? That's not terrible? Okay, we'll stick with that. So sepals are flower-associated covering garden petals, And then petals are independent of the flowers themselves. They just, they're leaves, right? So we are going to capture then the lengths of the sepals and the widths of the sepals and the lengths of the petals and the widths of the petals. And then we're going to record which species does this particular plant represent. Now I've noted that I've used my favorite, which is the summary function, but there are also a couple really valuable functions here called head and tail that certainly Linux users will be very familiar with. So if I say head iris or tail iris, I'm going to get different results out, but they have the same fields. You see that the head is showing us rows 1, 2, 3, 4, 5, 6, while the tail function is giving us the last 6 rows in the table. So if you're ever trying to just get a quick sniff of the data, summary is pretty good, but if you want to get a sense of what the data look like, head and tail are very good for us. And we note that these data have actually been sorted, that the setosas are all at the top, and the virginicas are all at the bottom, and in the middle we have the versicolors. Okay, so we could just tab through the data, etc., but for now, head and tail will do it for us. All right, let us now look at a scatter plot as generated by the rplot function. I'm going to start by just copying this code over. We see it's very, very wide, so I'm going to stick with this for just a moment. The plot function accepts data as its first argument. X here represents the set of data. So we are going to specify that on the x-axis, we're going to show the sepal length variable. On the y-axis, we're going to show the sepal width variable. We can provide information about what the labeling should be. So we're going to specify that the x label should be called sepal length, the y label should be called sepal width, and then the main is going to provide the label that appears at the top of the graph. So if I simply hit enter, boom, up pops our graph. We see sepal length and width appears in the main location. Here we've got sepal length, here we've got sepal width. Now, there are a couple things that happened automatically, and it's really worth talking about that. So first off, I note that the sepal length axis starts a little below 4.5 and ends at about 8. Did we tell the software what range of values we wanted to use for the x-axis? We did not. So the software has automatically decided for us. Did we specify that it should put a tick mark every 0.5 along the axis? We did not. But it chose an automatic setting that it thought would work out pretty well. And frankly, I think that's a very sensible choice. I would note also that this graph has a bit of a problem. What would happen if two plants had the same sepal length and sepal width? They would appear at exactly the same location on this plot, and it would be overplotting. It would have the same circle planted again and again on the same one. So this graph has some problems associated with it. And one of the things that I find irritating about this graph is that it ignored every field except for sepal length and sepal width. It did nothing at all about which ones were setosa, which ones were virginica, and which ones were versicolor. So this is fine for a start, and for a lot of the things you would do with this type of scatter plot would be great. Is there a problem with using these little O shapes for each plant? It's not terrible, but you might imagine a scenario where you wanted to use a bigger circle for one and a smaller circle for another, or an X or a plus or something like that. R gives you the ability to do stuff like that. But at this point, we've just used the basically one-liner to make this basic plot, and it's okay. It's okay. So let us now try for something a little showier. Next, we're going to use Ggplot. And remember, it's called the grammar of graphics. And the reason for this is that it specifies a way that you can have a conversation with the software about how to compose this image. So what we're going to do is start by creating an object called scatter. And scatter is going to be created by the Ggplot function. We're specifying to Ggplot that all of the data that are to be that it has access to within this plot are encapsulated in this object called iris. This is the big table that we were just paging through. We're going to specify an aesthetic, which is to say that we need to specify how the visual elements of the graph correspond to the data. So just as before, we're going to specify that our x-coordinate is going to be built around the sepal length field. The y-coordinate is going to be based around the sepal width. Now, before I said iris $ sepal length for x. Here I didn't do that. Does anyone detect why? I've already specified that all of the data from iris are available to the graphing software. So when I specify sepal length under the aesthetic, it already knows that it can look within the data to find the sepal length. So I don't need to specify iris $ sepal length anymore. Y sepal width is, again, drawing from the fact that it's part of the iris data structure. And finally, in aesthetic, I'm specifying that the color equals species. So the color is going to be coded for by the species. The software already knows that that's a factor with 3 levels. So there are not 150 different species. It's 3 different levels within species. Each one is drawn from that. Now, I note that this is not a single line. This scatter line by itself, if we enter that into R, is not immediately going to produce a graph. But that's because I haven't specified a geometry for this graph. So already, we've seen 3 different kinds of elements we needed to specify to produce this scatter plot. The data source, the aesthetic, and now the geometry. So I'm going to add that geometry here, and boom, now it has enough information to go ahead with the graph. So we see that Ggplot has already made a lot of choices differently than what the base thing did. So we don't have a main on this. There's no main label to this graph. We didn't tell it to put one on. The Y label and the X label are also different because it's just using the name of the variable itself. We didn't specify use this X label. It has also chosen a different number of grid marks, but its overall range is just the same. But one of the very powerful things that's happened is that because the Ggplot data includes the species, we were able to tell it, we want you to vary color as a function of species. And so we have our red points up here, representing setosa, a series of green dots here, kind of an unfortunate color palette choice, I think. The green dots are mixed in with blue dots, but they're quite similar in how they appear on the projector. So the software has helpfully indicated a legend here to represent which colors represent which species. So it's done a lot of automatic things for us very easily. Now, I use base graphics a lot in my R plotting. So it is possible, certainly, to present each of the subsets, setosa, versicolor, and virginica, in its own color within base graphics. You could do that. But I know that even if I were doing it, I would first need to decide what are the X limits and Y limits that apply for the entire graph before setting up that graph in the first place. And then I would want to, I would need to specify that these points should be added in color red, these points should be added in color green, and these points should be shown in color blue. I could do that. So this graph is doing a lot of the things that we would end up doing anyway, but doing them by default. And it's doing so because it has access to the whole data structure. Okay, I'm going to close this graph now, and we will return to this. So I've tried to give a little introduction here on the grammar of graphics. There are manuals upon manuals and frankly books that you can get on how to do Ggplot well. But I would try to say that we're constructing a figure progressively. The geometry is our specification of what kind of image to make from the data points. In today's discussion, we'll be looking at box plots, scatter plots, and histograms, because these are really common visualizations. Aesthetics give our way of relating the data to the elements that get displayed. Where does it appear on the x-axis? Where does it appear on the y-axis? What is the shape used for it? What are the labels associated with it? All of those fall under the aesthetic term. So I want to do a linear model that's been fit to those data. So scatter still exists as an object. Remember, we captured that by running the Ggplot function in the first place and storing it in scatter. The geom points add those dots of 3 colors representing the species. But now, by just leaving a plus on the end of the line, I can specify that I also want to add a geometry of a smooth that is representing a linear model showing a relationship between the x and y variables. So just as before, I'm going to do scatter and the geom point, but now the geom smooth is an additional feature that I'm going to include. Okay, so I'm going to just paste that in. And now look, we get a rather different look to this, don't we? So we note that we have an XY relationship between sepal length and sepal width. What does that mean in terms of a plant? If you have a correlation between the sepal length and sepal width, why would you expect to find such a thing? I'm going to give another example. What if you were to make a plot of all of the people at CPUT Bellville with height on the y-axis and weight on the x-axis? Is there a correlation there? Maybe we could make men blue dots and women red dots. We could make it pink. Would that be terrible? That would be terrible. All right, we're going to step away from that. Today, women are the blue dots, men are the pink dots. Are we good with that?
Yeah.
All right, good, great. So we now have 2 somewhat different distributions, because men still tend to be a little taller. Women tend to be not quite as tall. But if we just consider men for a moment, we note that very tall men also tend to be a little heavier in total weight. I'm not saying that they look chunky. I'm saying that there's more height to distribute that weight across. Short people tend to have a little lower weight, generally speaking. So if we were to, you see, I grew up as a short man. I didn't start growing until really, really, really late in high school. I was 16 before I started growing at all. At my 16th birthday party, my mom, who was 5'2", tiny, put her arm around me, around my shoulders, because I was a good armrest height for her, and said, "Oh, 5'2", and his eyes are blue," and I just wanted to slug her. I was so angry. I hated being short so much. So anyway, I retain this vision of myself as a short person for forever. So you can imagine then that for men and women visualized on this height and weight plot, that as you go to a higher height, you also go to a higher weight. And similarly, we see that sepals that are particularly long also tend to be wider. Okay, so we have a correlation in the data. This linear model is capturing that sepal length and sepal width. Great. Why does the linear model for setosa in red stop abruptly at 5.7 or so? There's no more data. That's the largest of all the sepals. So the linear model does not by default extrapolate beyond the range of the data as they exist. Now, is there a reason why, say, this blue line has a really, really wide ambit here, but not why is the blue gray the gray area for the blue fit line very wide? It's trying to do its best fit to include the data that are there. So if the data are very widespread around the trend line, so will that gray area. So it's kind of giving us like a confidence interval around that line. Okay, but remember that was just one more line of code, right? We just had to specify we wanted a geom smooth built around a linear model. The software figured out what we meant from that. Very powerful. Okay, so Ggplot allows us quite a lot of flexibility in making sense of our data visually, and doing so in a pretty simple kind of syntax, the language that we use to describe that. Now, I'm widely known in our university for screaming bloody murder when grad students and professors show slides of dynamite plots. Have you heard of dynamite plots? These are basically bar plots, right? So we have someone saying, I measured this experiment 5 times. I'm going to draw a bar up from the baseline to the mean value, and then I'm going to put something like standard error tick marks on the top of it. That's called a dynamite plot. I hate them. I hate them very, very much because they do a very, very bad job of showing variability. If you ask students what the tick marks mean on top of their dynamite sticks, they frequently don't even know. They might say, oh, well, that's standard deviation. And I say, is it standard deviation or is it standard error? And they frequently say, oh, it's actually standard error. I'm like, are you sure? Right, because people use standard error rather than standard deviation on their dynamite plots because it looks like their data are less variable. It's a bad thing. Okay, so when people have a distribution of values, I encourage them to step away from dynamite plots and instead use something simple like a box plot. So a box plot, in this case, is going to be operating within the base graphics environment, something that doesn't require Ggplot. And what we're going to use is a function, an equation. So the sepal length is a function of species. All right, we're making the assertion that different species have different characteristic sepal lengths. Again, we're going to specify that the data are coming from iris. We're going to provide the same X and Y labels, but this time we're going to specify that it is a box plot. Okay, so, our X label has changed to species this time. So when I enter this in, out pops our box plot. So the software has already remembered that the species is a factor, and there are 3 different levels: Virginica, Versicolor, Setosa. So each of those gets its own box plot. And here we're looking at the distribution of sepal lengths for each species separately. Typically, the way that we read this is to say that the middle line of the box represents the median. The lower and upper edges of the box are the 25th and 75th percentiles. And generally, these tick marks represent the full range of the data. But in this case, we have a data point that's well outside the box, an outlier on Virginica, so it is shown as a separate point. Okay, so that was not bad. The software, even though it's just part of the base graphics language, is able to separate the data out 3 ways and very, very rapidly give us this plot. So can we do the same thing within Ggplot? Yes, of course. Ggplot is now going to use to use the Ggplot function, working from the iris data, using X this time as species separation and Y as sepal length. And then we're going to add a geometry to specify that it is a box plot type with the aesthetic that we're going to fill the boxes based on what species color they are. All right, so I'm going to run those 2 lines. From the whispering, I'm concerned that this didn't run correctly on somebody's machine. Did it work? Oh, that's good. Okay, cool. So the box plot looks very similar to what it did before. We still have our outlier point. We still have our whiskers. The whiskers don't have little handles on them here, but that's not a huge difference. And we've got, of course, the use of color to help us understand that aesthetic. So Again, I think that by default, its behavior is pretty sensible and produces an image that we wouldn't feel too embarrassed about putting on a poster. I would probably want to do things like change these variable names so that they read sepal space length instead of dot length, but minor quibble there. All right. So we're going to add a statistical characterization here as well using the stat summary function within Ggplot. So how does that change the result? I had to provide some parameters here to specify points, etc. Let me see. All right. So does anyone notice how this changed from the image before to this one? Anyone see anything different? The diamonds. Right. So in this case, although the median was already shown as part of the box plot, we've added the mean values as well. So the mean values here are shown by the diamonds, and in the case of Virginica, they're slightly different. In the case of Versicolor, very slightly different. Okay, helpful. Let's see, and in that case, we can specify which function we wanted to add. You could, for example, add a minimum or a maximum, but we've specified that the function to be used from stat summary is the mean function. We also specified that it should use the point type of geometry and that it should be shape number 5, size equals 4. So you could set that larger or smaller to be whatever design you want it to be. Okay. The next plot I want to talk about is like a box plot, but it's really adding this very valuable type of visualization called a jitter plot. I'm going to go ahead and run it, but as we can see, we're again adding the geometry of the box plot to another geometry, the jitter plot. All right, so as we add that together, boom. So let's contrast 3 ways that we could visualize this. If we did this as a dynamite plot, we would basically have a bar going from 0 to 5 and then some whiskers on it. The box plot shows us the central part of the data through this, the interquartile of the data through the box and the range through the ticks on it. But now we've superimposed the actual data points on top of it. A jitter plot can hold an awful lot of data points. Even if you've got 100 values, you can still show them pretty comfortably. Here we have 50 values in Setosa, 50 in Versicolor, 50 in Virginica. But it doesn't look particularly crowded, does it? So it's very valuable to be able to overlay the original data points on top of this, along with the statistical analysis that the box plot itself delivers. Okay, so I strongly endorse the use of box and jitter plots to showing these distributions of points. All right. Now, we have already done a little bit of work with histograms. I think this is, okay, yeah. So we are going to do histograms, this time on the basis of sepal width. We're going to label that the y-axis becomes frequency, and we provide a meaningful title through the main feature. So here we go. There we go. Histogram of sepal width. Rapidly, we can see how these data are distributed. So we could ask, are the sepal widths uniformly distributed for each of these plants? I'm going to argue that that's not a uniform distribution. It's not level all the way across. Is it normal? It could be normal. It could be. Actually, deciding whether or not the data are normally distributed is a very difficult thing to prove unless you've got 1,000 data points. But in the case of these 150, I would say that at least they have one mode, and they're sort of symmetrical, except we've got this little tail up here. So maybe if we looked at them by plant, if we were to look at just the Setosas or just the Virginicas, we would notice that they were normal. Hard to say from this. At best, I would say we're adding 3 distributions there. So not necessarily the case. Now, if we were to do a histogram, we would again need to create our object of the histogram from the Ggplot, and we need to specify our aesthetic. Here, we are going to specify only that the sepal width values are going to be shown across the x-axis, and then we add our geometry to specify that we want a histogram. We're going to specify as well that we want the bin width. Remember that histograms require that we throw multiple plants into the same bins. We're going to specify the bin width is 0.2 in this case. All right. Is it beautiful? It's not beautiful. I actually don't think the histograms from Ggplot look great, but it is possible to do all kinds of amazing things with this, and we're going to look at some of those to prettify this a little bit. But this is the base histogram that comes out. All right. Nope. Almost closed my window there. I didn't want to do that. All right. So for our next stage, we specified more stuff to go along with our histogram. Before, we only gave a bin width, but this time, in addition to bin width, we're going to specify that the fill color, what we put inside the boxes, is going to be based on species. So let's try running this one. Okay, so this is the same as it was before, but now we're using what is effectively a stacked bar. We're asking how much does each species contribute to that particular range of values. We see that only versicolor is contributing to the smallest sepal widths. Only setosa is contributing to the largest sepal widths. But when you're in the middle of the stack, you actually have a collision of all three species. The virginicas, more virginicas are contributing to this bar centered on 3 millimeters than to any other bin width. Okay, so that is a really powerful thing to do to get a sense of how the species interplay with the different bins.
So for that, how do we include standard deviation?
How would you include standard deviation? In a histogram, it's not really clear how you would do that, because in the histogram, each bar is shown as wide as the bin width. So we could, for example, change this to be a bin width of 0.5. This gets a lot bigger grains in the visualization that comes out. You see how the number of bars shrinks a lot? Now each of these is 0.5 wide. So we could do that. We could make this much more finely grained by going down to 0.1. But of course this has the odd effect that the number of plants that fall into each bin is much smaller as a result. Now there are still quite a few that fall right around 3. But I would say that standard deviation is not necessarily a thing that you would use to understand a histogram. It's much more relevant to the box plots that we were just looking at. We had the option up here when we were looking at the stat summary for this box plot. I believe that we could have included standard deviation here rather than mean. I don't remember what the exact call syntax is, but I could look that up and add that there. All right. So we've done now a stacked histogram essentially to show us how much each species contributes. Of course, having it on screen is nice, but a lot of us would really like this to appear on our poster. Or we want to include this as our set of figures for a manuscript we're submitting. So for this, I would like to output our graphs to a PDF. Here we're going to create these scatter images. Where's the function? Well, all right. We're going to simply run this whole block of code because I don't think there's anything going on here that we haven't seen so far. We're going to use the linear model version of our scatter plot. We're going to use the box plot that includes the jitter. And we're going to include the histogram that separates out by species. But the thing that we're going to include at the top and the bottom is really important, so I want to spend just a moment with that. Generally speaking, the default device to which these images are rendered is the screen. But in this case, we're going to override that behavior by using the PDF function. We're going to use the default PDF output to output a file called output.pdf. So anything that would normally have been splatted out to the screen will instead be splatted out to a PDF with the name output.pdf. If you try to create the PDF and forget to close it off at the end, you won't be able to view it. So you have to start by saying, we're going to output everything that follows to a PDF, but at the end, we need to turn off that device, because otherwise we don't get a completed PDF. So let us now come over here and just paste that whole glob in here. At the end, we get this null device business. That's just the software letting us know that we have now turned off this device and we're back to default.
Why is it Windows 2?
Okay, that should mean that it's back to writing to Windows output. That's interesting. I wonder why it's different in the two. Ah, okay. So yours is using. Okay.
I'm using R, not RStudio.
Yeah. So RStudio is going to be used. You said it's
RStudio GD2.
GD.
And then underneath it 2.
Ah, okay. So yeah, the RStudio graphics device. Ah, so yeah. Sometimes you'll see stuff like that. Okay. So in this case, though, we should all have written a file called output PDF. Does RStudio actually show it in this project? Okay. I'm not sure where it's located then, but on mine, I can go to my documents, because that's the default directory where R will run, and I can simply open this output PDF. All right, so when I look at this, I can put it.
in documents.
Ah, it's in my documents. Okay, that's good. All right, so our first image is right here. If I scroll down, I see that the second one has been automatically put on the second page. And the third one appears on the third page. Now it might be that I want to do some added markup on this thing, that I want to have the graphic, but I want to put some arrows pointing to things. That's not that easy to do with a PDF file, is it? So we think of PDF as kind of a final output. So I might I might instead use something like PNG. Did I actually leave an example in there of the code? I didn't. Okay, so we're going to do a PNG at this top instead. PNG file equals output.png. We should really use more descriptive names than that. So now I'm going to grab that same block of code, this time using PNG rather than PDF, and copy that. Okay. So here we go. I'm going to just run that all through. I get the same null device at the end. I go looking in my documents folder, and there's output PNG. And so if I double click that, what do you notice has happened? The PNG format, at least the support for PNG format within R, does not allow for multiple pages, because this is just like a GIF, basically. So in this case, it would really have been a lot better for us to create a PNG, to open a PNG for each image, and then after the box plot, for example, have a dev off. So you'd want to use a different name. Ideally, the way that we would do this would look something like output 1 PNG, and now I'm going to say dev off here, and then I'm going to say output 2 PNG here, dev off here, and finally output 3 PNG. Great. Now I'm going to run that whole block. I'm going to close this too. All right. Okay, null device, null device, null device. Now we have 3 images that have been output. And if I come to documents, I can open this one. That output 1 is the dot plot with the linear model. That's output. Output 2 is the box plot with jitters. And output 3 is the stacked histogram. Okay. At that point, I can open it up in an editor and make it beautiful and special in all the ways that we know how to do.
But how do you copy that into your work? Those
Oh, well, I can open up Word. Hello, Word. Oh, I wrote a letter of support for someone yesterday. This is some text, and now this follows Figure 1. Now I'm going to throw in an image here. We all know that Word is very tricksy about how it adds in images. So I'm going to use a trick. I'm going to insert a text box. Oh, where is this? Insert text. They've changed it to me. Here, a text box. Okay, I'm going to use the simple text box. All right, well, I'm going to anchor it here. Okay. And I'm going to make this Figure 1. And now here, I'm finally going to go to the Insert menu, specify Pictures. Here it is. Now I need to go to Documents. Here we go. And I'm going to grab Output number 2, because I thought that one was pretty. All right, and I say Insert. There it is. Okay, clearly that's a little smallish, so I better resize this box. All right, and I want this one. I'm going to change that formatting. You see that? I'm going to make it full width. All right, and now I'm going to make this thing grow. Where's my corner? Here's my corner. Zip. All right, grab this little guy. Now, I note some people grab handles like that and they do this stuff. Don't do that. That will make my eyes cross when I'm looking at your poster. Don't do it. All right, grab this corner and then it scales together. It's actually something that you can address back here under Pictures, under Size. You can specify that it has a locked aspect ratio, and that should prevent people from stretching it inappropriately. All right. Well, so PNG is one way you can do this. You can also write Windows metafiles and things like that. But there are lots of ways to incorporate those images in this. Okay. So with that, I believe we're at the conclusion of today. I'm going to return this to its original shape. Okay. But hopefully you know a little bit more about how to do visualization within Ggplot. It is complex. There are a great many features within Ggplot that can allow you to specify that no, these bars should be very slightly separated from those bars and things like that. Picking what color palette you want to use, what font you should use for labels. You can fidget with these things endlessly. But I think that generally speaking, Ggplot represents the most typical way that today people visualize biomedical data. So I hope that you find that it is just as valuable for you. Great. Okay, we'll be back here tomorrow to talk about a whole bunch of t-testing. It's going to be a lot of fun. All right, see you tomorrow at 9 a.m.